Properties of curves, page 11. Suppose that the function e of x minus 3 and 3 minus 5e to the minus x, where x is between negative 3 and 4. Find the x and y intercepts of both functions. Okay. Let's see. So to find the y-intercepts, you insert x equals 0, and to find the x-intercepts, you find y equals 0. So let's try doing that. So we'll do that for f first. So f of 0 is equal to e to the 0 minus 3, which is equal to 1 minus 3, which is equal to negative 2. What if we set f of x equal to 0? Then we have e to the x minus 3. We have e to the x equals 3. And we have, let's take the natural log of both sides. Then we have x equals natural log of 3. Okay. So this is the y-intercept. This is the x-intercept for f. Okay. What about for g? G of 0 is equal to, and this will be the y-intercept, 3 minus 5 times e to the 0, which is 1, equals negative 2. Also negative 2. What about if we set the whole function equal to 0? So 0 equals 3 minus 5e to the minus x. 5e to the minus x is equal to 3. E to the minus x equals 3/5. Natural log of both sides will get negative x equals the natural log of 3/5. X equals negative the natural log of 3/5. So this will be the x-intercept, and this will be the y-intercept. Okay, so we found that. Discuss f of x and g of x as x approaches infinity and negative infinity. Okay. So f of x, when x approaches positive infinity, is going, and remember, this is all from like chapter 2, right? Except for in chapter 2, we didn't know the function e to the x yet, so it's a little bit different. So if we put infinity in for that, we would basically get infinity. What about negative infinity? If we put negative infinity, e to the negative infinity is like 0. So f of x, as x approaches negative infinity, is going to be equal to 0 minus 3, negative 3. Okay. What about g? G, as x approaches infinity, is, let's see, if you put x equals infinity there, you're going to get e to the negative infinity, which is 0 also, so you're going to get 3. And then if you do g of x as x approaches negative infinity, you're going to get e to the negative of negative infinity, e to the infinity, which is infinity, you get negative infinity. Okay, so that was b. Find algebraically the point of intersection of the functions. Okay, so to do that, you're gonna assume you have two functions, e to the x minus 3, and you have a function 3 minus 5e to the minus x. You're going to assume that the x's and y's can be the same at some point. And so since they're the same, we can set them equal to each other. E to the x minus 3 equals 3 minus 5e to the minus x. Let's see, 6 equals, we're going to add 5 there, so e to the x plus 5e to the minus x equals 6. A long time ago, we did problems like this. If you remember the Jinsel method. Okay, let's multiply everything times e to the x, which we can do easily because one of the sides is 0. So we're going to have e to the 2x minus e to the x plus 5. Because e to the x times e to the minus x is just 0. Now we have a quadratic, basically. We can substitute t equals e to the x. If we do that, now we have t squared minus 6t plus 5. This can be factored. T minus 1 times t minus 5 equals 0. So the solutions are t equals 1 and t equals 5. What is t? E to the x equals 1, e to the x equals 5. So x is equal to natural log of 1, x is equal to natural log of 5. Those are the two solutions. Since we want the points of the intersection, we need to find out what the y's are that correspond to that, so we could plug it into either equation. It could be that one. Looks maybe a little easier. So we'll have y equals e to the x, which would be 1 minus 3 equals negative 2. And for the other one, it would be, if we put natural log of 5 in there, we'd have 5 minus 3 equals positive 2. Okay. So these are the intersections that they asked us to find in C. Now it says to sketch the functions on the same set of axes. And we have a lot of information to graph here. Okay, so there's my axes. I'll do one of the functions in pink and the other one in some other color. So let's see, which one am I going to do in pink? I'll do, let's see, F. I'll do F in pink. So the y-intercept is negative 2. And the x-intercept is log of 3. Natural log of 3. On the offline calculator, I can see that natural log of 3 is about 1.10. So that would be about here. Okay? And let's see, the behavior of f of x as x goes to infinity is it goes to infinity, and the behavior of f of x as x goes to negative infinity is negative 3, so we're going to have an asymptote at negative 3 here. So it's going to kind of look like this. Okay, that's f of x. And let's do the other one in blue. So g of x, so the x-intercept or the y-intercept is negative 2, same point here. And the y-intercept is negative natural log of 3/5. Let's see, natural log of 3/5 is negative 0.510, and the negative of that would be 0.511. So 0.511. Okay, so it would be about there, right? Okay. And the behavior of g of x as x goes to negative infinity is negative infinity, and the behavior of g of x as x goes to infinity, positive infinity, would be positive 3. So this is our asymptote. So it kind of goes like that. Okay, and then the intersection points, remember, are these here. And they tell us that there's an intersection point at 1, or natural log of 1, which is 0. Oh, it's 0. There. So this is equal to 0, comma negative 2. So one of the, so yeah, we knew about that point. Double there. Okay, and natural log of 5 is 1.61. So there's a point that's 1.61 comma 2, which is about there. 1.61 comma 2, so it's about 1.61. It's like right there, kind of. Okay, you can see my drawing here is not very good. this one too. I need to go through that point. So let's see. Let's try the pink one again. Okay, and then the blue one. Okay, there we go. All right. First thing they ask us is the x-intercept for this function here. Remember, the x-intercept we find by setting the y value to 0. So let's solve this. Natural log of 2x minus 1 equals 3. E to the that. So we have 2x minus 1 equals e to the third. And then we have 2x equals e to the third plus 1. And we have x equals e to the third plus 1 divided by 2. Okay, and so that is the x-intercept. We can kind of find a rough value for that. Let's see. We'll do like e to the third plus 1. That gives us 21.1 divided by 2 gives us 10.5. Okay. So the x value is 10.5. That's where it crosses the x-axis. Okay, so that's the answer for A. Can f of 0 be found? What is the significance of this result? F of 0 cannot be found. And the reason why is if you put natural log of, and you put x equals 0, you're going to get a natural log of negative 1. And you can stop right there because negative numbers don't have natural logs. Okay? So, it doesn't exist. Okay. Find the gradient of the tangent to the curve at x equals 1. Okay, so to find the gradient of the tangent of the curve, we do need to find the derivative. The derivative of f is f dashed, and we could put 1 over 2x minus 1, and times the derivative, which would be times 2, and the derivative of negative 3 is nothing, 0. So we just found the gradient, or we just found the gradient function, and now we just need to evaluate it at x equals 1. We're going to get 2 divided by 2 minus 1, which is 1, which is 2. So the gradient of the tangent of the curve at x equals 1 is 2. Find the domain of the function f. Okay, we already know that negative 1, or 0 is not part of the domain. So what is in the domain? Well, remember, natural log exists for positive numbers. It looks kind of like that, okay? We can see here that we have it shifted to the right a little bit. So we want to know, where is this asymptote? Well, the asymptote exists at natural log of 0. It's natural log of 2x minus 1. So the 0 point is x equals 1/2. Okay, so at x equals 1/2, then that's when natural log would start to exist. So it's actually x is greater than 1/2 is the domain. Okay. Find the second derivative of f and explain why f of x is concave down for all x in the domain of f. Well, you can already see from looking at the log function that it's concave down for eternity here. So this isn't going to be like a big surprise or anything, but let's take the second derivative and we'll get we can say the first derivative is 2x minus 1 to the negative 1. So we could use the product rule, and we'll say 2x minus 1 to the negative 2. Oh, and it's also times, 2, right? Can't forget that. Okay. And so let's see. Whatever number, well, you can't put in any number smaller than 1/2. So like, if you put in 1/2, this would be, it would blow up in your face. The denominator would be 0, right? It would be 2 over 2x minus 1 squared. And if you put 1/2 in there, the denominator would be 0. That would be bad. But if you put in any number bigger than 1/2, then you would have a positive number. And you can never get a negative number because it's squared here, right? No matter what you put there. Okay? So that's why f of x is concave down because the denominator here is always positive. Okay, so it's always concave up because the second derivative is always positive. Okay, then graph the function showing all the features you have found. Oh my gosh, okay. So, I think I'm going to draw it so that, you just have, because we know it doesn't exist left of this point, x equals a half, right? So we have an asymptote here at x equals a half. And then, let's see. We know the y-intercept is 10.5, right? So we'll count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.5. So it's right there. Okay? And so we know the x-intercept. We put that. Can f of 0 found? We know we already used that. Can the gradient of the tangent of the curve at x equals 1? The gradient of the tangent of the curve at x equals 1 is 2. So it's about like that. Okay, that's the tangent to the curve. At x equals 1. But it's not necessarily at this height, right? It's actually going to be lower. Find the domain. We found the domain. Find f double dashed, and we know that's concave down. Okay. So basically we're going to have something like this. It's going to go through this point, right? And then we know it's concave down, so something like this. And then when it gets to the asymptote, it's going to be at a tangent of -2, just like this. Okay? So something like that. Alright, we can figure out 1 or 2 points by putting them into the original function, into this function here. We could put in like x equals 1. X equals 1 would give us 2 times 1, which is 2, minus 1, which is 1. The log of 1 is 0. 0 minus 3 is -3. So we can find out that this point is going to be right there. Hey, that's pretty much where we sketched it. Okay? So we got this point, which is 1, 3, and we got this point, which is 10.5, 0, and that's pretty 10.5, 0, and that's pretty much all you need to sketch this, right? And we know it's concave down. All right. That's it.